there is nothing new in terms of theory for this section. Okay, we've learned all of the information. It is just applications. How can we use what we've learned? So we're just going to do a bunch of different examples. Example number 1. Find the values of b and c so that y equals e to the 3x plus bx plus c is a solution of that differential equation that is written there. Okay, so what I'm going to have to do is I'm going to have to sub that first equation into the differential equation. To do that, I'm going to have to differentiate it because I need a y dash, right? So that first equation, I need, where's my pen? There it is. I need y dash. Differentiating e to the 3x, we get 3.
3x.
Very good. Differentiating the bx,
5.
we just get b, don't be silly please, and the c disappears. So I'm now going to sub that into the differential equation. So my differential equation starts with y dash. And what I'm going to do is I'm going to have an equation. I don't want y's in it, basically. I'm going to try and get everything back down in terms of x. So y dash is equal to the 3e to the 3x plus b that I just found. Then that's equal to 3y, but as I said, I don't really want the y in there. I'm going to replace the y with the original y equation, which is e to the 3x plus bx plus c, close bracket, and then minus 18x on the end. And what I'm going to do is I'm going to compare the different coefficients so that I can work out the b and c that are in there. Okay, so first of all, let's expand out those brackets. We have 3e to the 3x plus 3bx plus 3c minus 18x. And you might even want to collect up your two x terms. You can't add them because you have one of them has a b and then one of them doesn't. But I could put them together by factorising the x out. So I'm going to go plus x, which means I'd have a 3b minus 18 that both have an x that I can bring out of them. And then the plus 3c, I'm just moving that along to the end. Yeah, with me what I've done so far?
I'm just factoring.
Just factorising the x out of the second and the fourth term. Okay, so as I said, we're going to compare the coefficients. If I look at the e to the 3x's, they're actually identical. I have e to the 3x on the left and 3e to the 3x on the right. They're exactly the same. I get nothing from them. So there's nothing useful there. So I'm going to start with the coefficients of the x terms. So the coefficient of x on the left-hand side, there is no x term, so that means it's 0, correct. On the right-hand side, my x term is the one with the bracket there, and the coefficient is the 3b take away 18. So I can now solve that. I can work out what b is. So let's...
What happened to the b on the other side?
I haven't used it yet. I'm just looking at x terms. That b doesn't have an x on it.
Oh, yeah.
So I'm just looking at x terms on the left. There wasn't any. X terms on the right was the 3b minus 18. So solving it, I get 3b equals a positive 18. Dividing by 3, b is equal to 6. Okay, so I've got one of them. To find c, if we need to find the value of b and c, which is what the question was, then it does matter. Yeah. Okay, so we have to find the we're going to find the coefficients or equating the constants. Okay, the constant on the left-hand side of my equation is the b. And on the right-hand side of the equation is the 3c. So that means that b is equal to 3c. But luckily I already know what b is. It's 6 equals 3c, which means c is equal to 2. So the original equation up there would be y is equal to e to the 3x plus 6x plus 2. But we weren't actually asked to write the equation down again. We were just asked to find the value of b and c, which I have done. Okay. Part B. Find n so that y equals 10 cos nx is a solution of the second order differential equation y double dash equals minus 49x. So same kind of approach. I need to find from the y equals 10 cos nx, I need to find the second derivative. So we're differentiating trig here. First derivative. Who wants to have a go? Good. So cos differentiates to negative sign. The n from the x needs to come out the front, changes to sine of nx. Second derivative. Yeah, so negative 10, another n will come out, so it'll be n squared, and it's back to cos of nx. Yeah? Okay, then let's put it in, sub it back into our differential equation. Okay, so the differential equation starts with y double dash. My y double dash was negative 10 n squared cos nx. That needs to be equal to negative 49 y. But instead of y, I'm replacing it with my y equation, which will be a 10 cos nx. Okay, so if I multiply the negative 49 and 10, I have negative 490 cos of nx. Oh, I was going to cancel the cos nx first, because there's cos of nx on both sides. I'm going to we're basically equating the coefficients of the cos of nx. So we can say, hence, the negative 10 n squared has to be equal to the negative 490. The minuses will, of course, cancel out. Yes, dividing the 10 across the other side, we will get n squared equals 49. Not just 7, plus or minus 7. So n equals plus or minus 7. So I found n, which was what I was asked to do. If I was asked to write down the equation of y, it would be 10 cos 7x, or y equals 10 cos negative 7x. But that is actually the exact same equation, because cos is an even function. So by subbing a minus in there for the x, you're actually getting the exact same result, right? Okay, next one, question 2. Actually, question 2 and question 3 kind of go together. So this will be a long one, this one. The rabbits on Bandicoot Island are increasing. 50 years ago, there were 100 rabbits released, and now there are 10,000 rabbits. Assume in this example that the rate of increase of rabbits is proportional to the number of rabbits. Okay, it's an applications question. How are we going to use this? Okay, let's read through it again. The rabbits on Bandicoot Island are increasing, so I'm going to say this number of rabbits is going to be I'm going to call it n, the number of rabbits that we've got there. The 50 years ago, that's a time frame I'm going to be able to sub in to help me find out some of the constants that are in there. But the bit that I have to work out first is assume that in this example that the rate of increase is proportional to the number of rabbits. That gives me a differential equation to start with. It is saying the rate of change of rabbits, so that's the derivative dn changing with time. That's the rate of change of rabbits over time, right? That is proportional to the number of rabbits. So don't write this down yet. Proportional would mean proportional to n, like that. Not t, k. Proportional doesn't mean equal. If it needs to be equal, then I need to times some constant in there. That's my constant proportionality, right? So that is my differential equation to start with, so you can write that one down. Now, interestingly, just a little bit to note that n equals 0 would solve that differential equation. But continuing from there, I want to now get an equation for n, which means I'm going to have to separate my pronumerals in there so that I can integrate. Okay, so let's move the n components over to the left. So it will be 1 over n dn equals, I'm going to leave the constant over there on the right, n times the dt across. Okay, then we can integrate. So let's put our integral sign on both sides. I'm going to integrate those. So integrating 1 over n, we get log of the absolute value of n. Yes. Integrating ln log base e. Well, yeah, okay, we do to integrate properly, but yes, it will effectively disappear when I change my constant out. But we do it properly. Okay, integrating k. kt, excellent, plus a constant. C is our favourite constant to start with.
I suppose KT, yeah, still.
All right, to get rid of the logarithm part, that's a log base e. So we slide the base e across the other side and it becomes e to the kt plus c. So this should look familiar from the last exercise that we were doing. Then we are going to get rid of the absolute value part, which means that we would have a plus or minus over here on the right. And at the same time, we can split the e to the kt with the e to the c because we're splitting our constants out of there. Then we're going to take the plus or minus and the e to the c, they're the constants. Let's replace them with a different constant. Let's start with a because we're going to need a few. So we're going to start with a e to the kt, where we are just replacing the a with plus or minus e to the c. So a can be any constant as long as it's not 0 because we need some exponential growth here. Okay, we were then told some information so that we can work out the value of a, and that's right. So the first bit of information was that 50 years ago, there were 100 rabbits. So we're going to say that that 50 years ago was our starting point, right? That's when they started. That would be time equals 0. So if time is equal to 0, that's going to be 0, 100 that I'm subbing in. That's the t value. The 100 represents the number of rabbits. That's the n when I'm writing them like that. So sub those in, we would get 100 equals ae to the 0 times, because it's k times 0, so it's just 0 up there. And we found that a is equal to 100. No surprise there because it was just the basic exponential equation. So that a should have been our starting number, which was 100. But remember, if we do have a different type of equation, that it's not always, we'll see one of those coming up. I won't talk about that yet. All right, so far we have n equals 100 e to the kt, right? That's what we've got in our equation so far. What other bit of information have I been given? The 10,000 rabbits, and that is after how many years have passed? 50 years. So now I'm going to sub in that if t is 50, I have 10,000 rabbits. So n is 10,000 equals 100 for the a, e to the k times 50, or 50k. And I have to solve that equation. So divide the 100 away, and we get 100, because it's 10,000 divided by 100 is 100, e to the 50k. I'm going to go over here because I'm running out of room.
So just do log.
Yes, so now we do a sliding base. We keep the 50k, we slide the base e across, so log base e, or ln of 100. And that means that K is going to be equal to ln of 100 all over 50. I'm going to leave it exact, correct? Okay, so my equation is y equals 100 e to the ln of 100 over 50 times by t. Bit of a nasty constant, but at least it's exact. And there it is. Part B. Find how many rabbits there will be in another 25 years. Be careful.
So
What am I subbing in? T equals? Yes. Okay, because remember we started, it says 50 years ago, so 50 years have already passed. We now need to sub in that T is equal to 75. No. Yeah, you can just say that. So if T equals 75, subbing into my equation for Y, actually that should be an N. Why did I change that to a Y? That was the number of rabbits. N, number of rabbits, equals, sorry, N, number of rabbits. It's just habit to write a Y equals equation all of the time. N equals 100 e to the ln of 100 over 50 times by 75, and you can have fun typing that into your calculator. Yeah, good job. So there'll be 100,000 rabbits, and then do the same thing again for 50 years, which means we're subbing in T equals 100. So all that does is add an extra 0. It's 1,000,000. So perfect. Because of the very nice numbers that we got to sub in. Yeah, the ln, the base E and the ln would cancel out, assuming that you brought that 50 up and to be a power. If you rearrange the logarithm, you could do it. ln and the base E would effectively cancel each other out. Okay, so, yes, yeah. I did. I've got to stop writing Y. Thank you. No. All rabbits, obviously. Interesting. Next
Now
question.
we're limiting something.
Kind of not as morbid as your suggestion, but
So
yes. All right, quickly. Yep. We can move on to the next
with
bit.
if you could go, what if we said plus 100? Could you still the E and the ln still cancel each other?
As in the plus 100 is on the end of the equation.
Is it the end of
Right.
the
On the power?
Yes.
In the power, no.
You could not cancel
No.
off because
You'd have to.
technically
Yes.
that's one whole number.
All right. So on that note, thank you, Benjamin. In the second question, it's not actually. Hey,
Babies.
enough. No gory stuff. Thanks. In real life, you can't actually have a population of rabbits growing exponentially indefinitely. I know it kind of seemed that way when rabbits were introduced. There was a lot of exponential growth there for a long time. But in any environment that an animal is introduced into, there comes this point where there needs to be this natural equilibrium. They've reached the saturation point, if you like, of how many rabbits can support that environment, and they have to naturally head to kind of a maximum population that can be allowed. So that's what this question 3 is about. It's the same question. We're still talking about Bandicoot Island. It says that it is estimated, though, that the maximum carrying capacity of Bandicoot Island is 20,000 rabbits. Okay, so it is increasing exponentially, but it's going to get to that point where the island can no longer support any more rabbits than that. Okay? So some of them would die if there wasn't enough natural resources to support them anymore, that kind of thing. No, go into a bend. Anyway.
Lifespan is
So this is perhaps a more realistic type of equation to use. It says use the population values in the previous example. So we're still going to use that 50 years ago there was 100 rabbits, that kind of thing. But modeled by this population growth, we're going to use this equation here. dn over dt equals, there's the kn that we had before, but the p minus n, that is talking about, that p is that maximum population that our exponential is approaching. Okay, so before we can do the differential equation part of it, we need to do a fraction decomposition again.
Will it be giving us the logistic equation inside a test?
Often they will, usually they will, yes.
And what happens?
They would have to give you some kind of information in it. So they're kind of hinting at it by saying that it is heading towards a 20,000 rabbits. So it is saying there. I think they will, but I'm not going to say 100% every time they're going to give it to you. Okay, so we did one of these before. Knowing that we're going to have to integrate this equation, we need to split apart that expression into parts that we can integrate. So the easiest thing to show that those two things are equivalent is to start with the right-hand side, push the fractions back together and show that it goes back to the left-hand side. So right-hand side is equal to the 1 over p bracket 1 over n plus 1 over p minus n. That's what we're starting with. I'm going to leave the 1 over p out the front and I want to add those two fractions together. To add them together, I need a common denominator, which means I would times the n with the p minus n. The first fraction, which had the n on the denominator, I would have to times the p minus n to the top of that first fraction. The second fraction, what do I have to multiply? No, it has the p minus n. What do I need to multiply to it? Just the n. So I need to go plus n for the second fraction. Okay, so what is happening is this, yeah, okay, you got it. All right, so I'm still that has been times with the 1 over p that is out the front. The the minus n plus n disappears, and we have also got a p on the top, and because p is the only thing left on the top, it would actually cancel that p on the bottom down there. And all that is left is 1 on the top over n bracket n minus p on the bottom, which is our left-hand side. Okay, so we've shown that those two things are equivalent, which is going to help us when we integrate. So part B, find the equation for the population, which is n, at time t years after introduction. Okay, so our differential equation is dn over dt equals kn bracket p minus n. Okay, that's our starting equation. Just like we did before, we're going to separate the parts so that we need all the n components over on the left and everything else over on the right. So that means I'm going to have 1 over, I'm going to have to divide the n over, and I'm also going to divide the whole bracket, which is the p minus n, because it has an n in it, right? I need to divide it across the other side as well. The p is just a constant, so it's not a problem here. That's going to stay with the dn. The only letter left on the right is the k, and I'm timesing the dt across to the other side. Now we know that we need to integrate this. I need to integrate that side and that side, but I can't integrate a 1 over n bracket p minus n. Okay, so this is where the partial decomposition part comes in. We want to split that fraction to be the integral of, where was my fraction? It was 1 over p. Now 1 over p is a constant, so it might even be easier to put the 1 over p at the front of the integral sign. And then we have 1 over n plus 1 over p minus n after my integral sign. Does that make sense? And that would be, I'm integrating that with respect to n, and on the right-hand side, I still need to integrate my k with respect to t. Okay, so we're ready to integrate. The 1 over p sitting out the front. Integrating 1 over n, I get ln of absolute values of n. Integrating 1 over p minus n. There's a small problem. Yeah. The minus n on the bottom, remember you need the derivative of the bottom on the top. So the derivative of that minus n is a -1. So I need a -1 there, which means I need to change that sign there to balance it. Right? So when I integrate the -1 over p minus n, I will get the negative from the front, ln of the absolute values of p minus n. Yeah, okay? Well, I can't just add a minus sign into my equation. I've got to keep it needs to be equivalent to a plus. My equation was a plus. So 2 minuses make a plus. So if I put 1 minus on the top, I balance it by putting the minus at the front of it to make it the plus that it was meant to be. Oh, that was from up here. That was part of my equation. So I had a 1 over p, and that was from my fraction decomposition. Okay, integrating, I need to close my bracket, sorry, and then integrate the other side. So integrating k, we get kt plus our constant c. Now we did have one of these the other day. We have 2 logs in there, they're subtracted. So I'm going to push, using my log laws, it becomes logs divided, that's right. So we're going to leave the 1 over p out the front still. And we have ln of absolute value of n over p minus n. And that's equal to kt plus c. All right, I've got to get rid of the p, I've got to get rid of the log, I've got to get rid of the absolute values. I'm trying to get an equation just for n here. By the way, hope you're writing small. I had to do that. I've got an extra page. I've got an extra paper here, if anyone feels I don't have enough room. Yeah. Okay, so times the p across first. So ln of n over p minus n. I'm going to just times the p over to be p times the kt, and p times c. Yes, I know I could, they're just making another constant there, but I'm not going to change it yet. I'll fix that all up in a bit. Okay, then I want to get rid of the logarithm part. So I'm going to leave my absolute value of n over p minus n. And I'm going to slide my base, which is an e. And I'm going to be e to the power of kpt plus my cp. No, you probably wouldn't be. It's better to write it and just switch out your constants. You're saying where you're switching them out. I'm just going to do it once rather than change it every time I multiply another constant with another constant. Okay, let's get rid of the absolute values. So n over p minus n equals plus or minus e to the value power of pkt, and let's split it e to the power of cp. Even though there's probably some more multiplying to be done here, I think we're getting way too many constants. Let's get rid of a few. So let's change that to be a. Let's go a e to the pkt, where I'm just swapping out that the a is equal to plus or minus e to the cp. All right, still not done because I need to get n by itself. And that is a little, it's going to be a bit more of a problem than we think because there's 2 n's in that equation there. So let's times the denominator across the other side, and we would get n equals p minus n, sorry, capital N, times the ae to the pkt. Now, if I expand that out, that's p a e to the pkt minus n a e to the pkt. You've got to be careful because you miss a letter, it'll wreck everything. Okay, I want both of the n's together so that I can factorize them out. So I'm going to move the second term there on the right, I'm going to move it across the other side, and I'll get n plus na to the epkt equals pae to the pkt. All right, factorize the n out, and we will get 1 plus AE to the PKT, not changing anything on the right side. And hopefully you can see what's happening. I get the n by itself by dividing that bracket across the other side.
You already put the n by itself.
No, I didn't. There's two of them.
Oh, there was two of them.
And I need one. I need an n equals equation.
Good luck to anybody subbing in.
All right, now do you remember having one? Oh, I switched the letter order there. It doesn't really matter, but just to keep it the same. Okay. Remember we had one of these the other day where we had it wasn't those exact ones, but it was an exponential on the top with your constant exponential on the bottom, and we said preferably we would like to simplify it so there's only one constant in there. So let's do that again. I'm going to divide by the AE to the KPT to try to just simplify that expression a little bit. So that means on the top, if I divide by the AE to the PKT, I'm just going to have a P left on the top of that fraction.
Wait, do we have to divide both sides?
You've got to divide the top and the bottom.
Both.
So I've just done the top so far.
Do we have to divide n as well?
Correct. Yes.
Okay, why didn't you times it then?
Because that wouldn't, I guess I could times it by, no, that'd be really weird. Yeah, 1 over, yeah, more complicated. Yes. Okay, so the 1 is often the tricky part. 1 divided by the AE to the KPT. Yes, it would become, the exponential part would become e to the negative KPT. And we would have a 1 over A. Let's change it to a different constant. B E to the, yes, B was, I'm letting B equal 1 over A. That's all I'm letting that do. Or A to the negative 1. Yes, I haven't finished yet, because then I have my second one where I'm doing AE to the PKT divided by AE to the KPT. Tongue-tied. 1. It's the same thing. Okay, we have an equation. Woohoo! If only that was all we had to do, because that's how much I had space for. So we are now meant to go back and find all the constants that are in that equation with the information that we've been given. Hence why I needed a second page when I wrote this out in my booklet.
Well, I'm already
Okay, so I'm going to go sideways. Oh, wait, you finished writing that down?
I can also
T equals infinity. No. Yes, we would, because that's what it's approaching. But that's not what we're putting in. All right, ready?
That equation looks awfully similar to the limiting sum formula.
Okay, so the information that we have been given. We know that our population is 20,000. It's approaching 20,000. And we knew that from the previous question, remember I said this is following on from the previous question, that when time equals 0, the number of rabbits was 100. That's what we had from question 2. So if we sub those into the equation that we have, we would get number of rabbits is 100. The population is 20,000 over D we don't know, E to the power of all those letters, but T is 0. So it doesn't actually matter what all the other letters are. That would be 0 up there plus 1. So this is going to let me work out what D is equal to, because all the other letters have disappeared temporarily. Oh, sorry, yep. So I used B. I used a different constant. I did it in here. There you go, B. It is a B. We are. No, we're not. We're typically. Okay, so times your denominator across. Yes, it does equal 199. So timesing it over, you would get 100 e to the 0 is just 1, so we'll just go b plus 1 equals 20,000. Then we are going to divide the 100 across. So we get b plus 1, we'll take 2 zeros off and we get 200. And then we subtract the 1 and b is equal to the 199. Okay. So far we know that our equation for n equals the population, which is 20,000, over 199 e to the negative kpt. I'm not going to put the 20,000 in there because that's too many things. I'll leave that p in there, plus 1. What else do I know about this population? Yes, it would be. But I just didn't want to write it in there because there's too many.
Oh, this looks like this looks frighteningly similar to a limiting sum.
So from question 2, we knew that when 50 years had passed, there was 10,000 rabbits. So we can use that to then work out k. Okay, so it's all just manipulating logarithms from here and subbing things in. So we have 10,000 equals 20,000 over 199 e to the power of, we don't know the k, but we know it is negative 20,000 for the population and 50 for the time and a k on the end of that. No, the negative was in the formula because the formula has a negative kpt. The 20,000 is because the p on the top was the same as the p and is always 20,000. I just didn't, you could write it in here, but I was just trying not to make that equation too messy. So that p in there is still 20,000 and the time was 50. And we still have a plus 1 on the end of that. All right, have a go. We want to get k by itself. Times the whole denominator across the other side is what I did. Or you could take the reciprocal if you're doing the Venn thing. But
that sounds like
negative 20,000 times 50 is negative 1,000,000 k. Okay, dividing the 10,000 across. You get 2. And then subtract the 1. Can I just go cancel that off and go 1 so I don't have to rewrite it? No? Okay. Then divide the 199 is 1 over 199. Then you're going to flip it, are you? All right, okay. So get rid of the negative. You're going to go e to the 100,000 k equals 199. That will save us some... Oh, yeah, sorry, Mr. Zero. I did, so that's why I copied it wrong from that one. 6 zeros, got to remember all my zeros. So then do a sliding base. So we have 1,000,000, 1, 2, 3, 4, 5, 6, k equals ln to the 199. And then divide your million across. Now this is keeping everything exact, which is preferable.
Yeah, so we have to write this all out again.
No, what I'm going to do, because the things that we've found are very messy expressions, what you can do is you can just say n is equal to p over be to the minus kpt plus 1. That was our equation. But then you just say what each thing is. So we know that p is equal to 20,000. we know that the B is equal to 199, and we know that the K is equal to ln of 199 over a million.
Doesn't that equation look really frighteningly similar to a limiting sum formula?
Yeah, I mean, they both have numbers in them, so it's even.
Yeah.
KD is interesting, LN1 times 15 instead of.
Oh, they would, wouldn't they? Because it's a
Oh,
million.
yeah, we want to cancel the 99 in the logarithm with the.
No, they are a million. 20,000.
Oh, yeah, absolutely. That would cancel out a bit, for sure, if I want to sub them back in and put them in the top there. All right, so question C, we're nearly finished. We want to sub some stuff in. Oh, go back to that side. Back here. Okay, question C. How many rabbits will there be in another 50 years? So we did this before. What are we subbing in? That T equals 75. Start with 50 years. I thought you said 50. Okay. N equals, you can have fun simplifying all this down. We have the population over 199 e to the minus, and here comes all the constants. So there's ln of 199 over a million times the 20,000. So yes, you could cancel some zeros from the 20,000 and the million there. And we have to times that by 75 as well, plus 1. You want to try typing that in? 18,000 is what you said? Yeah, yep. This is the simplified one. It's 199 e to the minus 1.5 ln of 199. So that's the simplified one you can type in, because the 20,000 divided by and the 75. So that should equal 18676 rabbits. Okay, you don't have part of a rabbit if you want. All right, do it again for 50. You want to do it all again for 50?
Well, we want less rabbits, so round it down.
Should be rounded down. So n equals 20,000 over, here it comes again, 199 e to the,
What's an Isaac?
excursion.
Oh, what? L. I was trying to do one dance, but I got a different line.
All right, you should get 19900 rabbits. Okay, that's rounded. Isn't that rounded? Exact. Does it cancel out? No. Oh, because the 100 came out nicely. There you go. Okay, the one last one is the D. Comment on these results in comparison to question 2. So we kind of talked about this when we were going into the question. Yes, there's a lot less rabbits, because in the first model that we did, we were just letting these rabbits increase exponentially indefinitely, which is not really realistic. Okay, so in the second question, the population increased like a geometric progression. It increased indefinitely, but this one, we are increasing to a limit of 20,000. So just write a little note in there. So in question 2, the population increased, well, they're both exponentially, but one's an exponential approaching and tapering off, and the other one's increasing indefinitely. So we probably say as a geometric progression, so timesing the same constant over and over and over. Whereas in question 3, the population approaches, a limit, yes, of 20,000.
Can we start with real? There's only 200 million rats in Australia.